Okay, finally I want to look at the expansion of the universe as a whole. This is sometimes in the field that we call cosmology, and of course we're dealing here with combinations of huge numbers of galaxies. Remember, galaxies can form into little groups, and then you can have superclusters. But then the superclusters are also connected together by mysterious forces that are related to something that we don't understand very well, dark matter. And so we're going to talk about these things in this last section. And so the expansion of the universe then begins with the Big Bang, as we saw in our first lecture. And this we think happened about 13.7 billion years ago. The best evidence we have for the universe being an expanding universe is the Doppler redshift. Okay, and so what we do then, the Doppler shift is an apparent shift in the frequency of light due to relative motion between the source and the observer. Okay, and so this then, if we were to do it with sound, then it would be a shift in the frequency of the sound. So you could imagine, say, a train moving toward you. But you know that the engineer of the train isn't changing the pitch of that engine for your benefit. This must be due to a relative motion between the source of the sound and you listening to it. And so that kind of, you can say the sound is to light as pitch is to color. Okay, and so if I'm hearing a higher pitched sound moving toward me and a lower pitched sound moving away, then we can say that that's a lot like the pitch of light. If a light source is moving away, it's going to be shifted to lower pitch, or red. So this is the lower frequency of light than blue is. If the galaxies were moving toward us, then we would say that it's blue shifted. And so how do we measure what light is what? Maybe we're seeing some red, we're seeing some blue. How do you tell the difference? Well, what you need to do is look at the spectrum of light coming from hundreds of billions of stars in each galaxy. And so here you see spectral lines, which are the frequencies of light that are coming from two specific kinds of elements, hydrogen and potassium, that are in the hundreds of billions of stars in this Virgo galaxy. Okay? And so this Virgo supercluster galaxy is very close to us, so there's not a lot of shifting of these known lines. And so what do I mean by shift? I mean that it's shifted from what it would be in the laboratory. So we know what the frequency of the hydrogen and potassium should be in the laboratory. And it's been shifted a little bit to the right, or toward the red. Okay, so to the right in this picture, it's just shifting toward the red. So it's like a police radar gun. When it clocks you moving, there's a little computer program in there that figures out what your speed is. And so we can do the same thing with these shifted lines. So we see then that Ursa Major galaxy, those same two lines are shifted farther to the red. And so that corresponds to a faster speed with which those galaxies are moving away. For Corona Borealis, even more of a shift. But you can see those same two telltale lines shifted by greater and greater amounts based on how far away the object is from us. And so not only can we tell that the universe is expanding because of the Doppler redshift, but we can also come up with another astonishing fact. The observational evidence shows that the farther away the galaxy is, the faster it's moving away from us. Galaxies that are farther away from us are moving away faster than more nearby galaxies. And so how can we explain that? How can we explain that not only are the galaxies flying apart, but the farther out we look, the faster they're moving away? Well, it's obvious, isn't it? Our galaxy must be at the center of the universe, right? Out of the trillions of galaxies in the universe, ours is that one special galaxy that's at the center. Everything's moving away from us because we're the most important. Just kidding. That was a mistake that was made by the Greeks. Remember, the Greeks put themselves in a position of exaggerated importance. And yet, how else could you explain it? I mean, it kind of seems like, well, maybe that is true. But scientists aren't willing to make that kind of a mistake. Again, we did that before. And so what we look for now is a theory that explains what we're seeing, but that could also be seen from any other galaxy's point of view, so that we're not putting ourselves in a privileged position. So the best explanation that we can come up with for this is that space and time are stretching. So you thought that I was explaining general relativity to you just for black holes. No, we need it for the structure of the whole universe too. And so here's our Big Bang. Now imagine for a moment that our universe is the surface of this balloon. So we start blowing the balloon up. But imagine that our existence is on the surface, the two-dimensional surface of this balloon. Okay, now, what's really happening is that this is a hypersphere, we think. And our three-dimensional surface is on the surface of a four-dimensional balloon that's expanding through the time dimension. But I can't show you that, so I'll show you this instead. Just imagine that we painted these little dots on here, and these dots are galaxies. So the Big Bang then is when this whole universe was completely deflated at time equals 0. And we start blowing up the balloon, making it bigger and bigger. But as we do so, the shape of the dots remains the same. But the spacing changes such that if you look out this far, this dot will be moving away from you that fast. But if you look out a little farther, that dot will be moving away from you faster. And so no matter which dot you look from, this dot will be moving away faster from this point of view, but this dot will be moving away faster from that point of view. So every dot sees all the other dots, or if you don't like that analogy, imagine raisin cake, blowing up the raisin cake. Every raisin sees every other raisin is moving apart from it, but the farther away raisins are moving away faster because there's more cake between a more distant raisin and u than there is a less distant reason. So this then explains, if we just think of the space as stretching, as the universe evolves. Then every star will be moving with ever increasing speed away from every other star with ever increasing distance. Okay? And so this then is Einstein's model applied to a stretching space-time. Okay? And so how fast is it stretching? Well, that's defined by the Hubble constant. It's given the symbol h, and we don't know exactly what it is. There's some debate about how fast the universe is expanding, but we think it's somewhere on the order of maybe 50. I'll use numbers that are easy to work with here. It's probably a little higher than 50, but 50 kilometers per second per megaparsec. Where a megaparsec is equal to 3.26 million light years. Okay, and so 1 parsec is equal to 3.26 light years. And it is basically just the distance that corresponds to you sweeping out 1 second of arc at a certain standard distance away. Okay, and so there's a definition for it, but here we can just think of it as being on the order of millions of light years. So the meaning of this then is, let's say this is our Milky Way galaxy. And this is, I don't know, just some distant galaxy. And let's say that this is 1 megaparsec away. Then this galaxy, on the average, will be moving away from us at 50 kilometers per second. That's about 30 miles a second. Okay. What if we go, and it doesn't matter which direction. I could put it over here, and I don't have to make it a spiral galaxy either. Then this is 2 megaparsecs. Then this typical speed would be 100 kilometers per second. If I went out 10 megaparsecs, I could go this way, 10 megaparsecs. Then this one would be moving away. Well, each time it increments by 50 kilometers per second. So if you go through 10 of those, it'd be 10 times 50, or 500 kilometers per second at 10 megaparsecs away. Okay, so just expanding this out then, and that's just the distance from our galaxy. And so a lot of this then is based on us understanding exactly what the size of the Hubble constant is. Turns out that if you work this backward, you can get the age of the universe. Because that's basically like taking this expansion rate and running it in reverse. And so the reciprocal of the Hubble constant is what gives us an expression for the age of the universe. Okay, and so there's an equation for this then. We can say that the velocity of the galaxy away from us is equal to the Hubble constant times the distance. Okay, so this is how fast the galaxy is moving away from us. This is the Hubble constant, and this is the distance in megaparsecs. Okay, so you can just plug in those numbers and you can see that 2 times 50, if I gave you 50 for the Hubble constant, will be 100. And so that's what we've got here. Okay? or 1 times 50 would be 50. 10 times 50, here this would be 50 kilometers per second per megaparsec times 10 megaparsecs. That would give us 500. So we can get the velocity of recession of the galaxies from the Hubble constant using this relationship, V equals hg. Okay, and so as we get more and more refined versions of the Hubble constant, we will be able to estimate these velocities better. So the question then, though, is, if this is all true, then what do we expect for the universe in the future? Well, there are different future possibilities for the universe. Let's just get rid of everything except for our expanding universe in this multidimensional space. Okay, and so in the future then, what will happen? Well, there are two possibilities. One is that the universe will expand to a maximum size, and then gravity will take over, and it gets smaller again. And then in the distant future, we'll have a big crunch. And that big crunch might, in fact, be the Big Bang for the next cycle. And so that is a possibility. Then when we ask, well, what happened before the Big Bang? Maybe it's just the end of the last universe. And that it's just this natural cycle of things that expands and contracts like this. And so that's one possibility then. The universe expands to a maximum size. Then contracts. This is true, then we live in what's called a closed universe. And a closed universe is finite in space and finite in time. What do I mean by that? Well, this balloon only gets to a certain size. And so that means that this three-dimensional surface is curved back around on itself. So that if you moved in any direction, you would eventually come back around to your starting point. And this curve, but this would be curved through a higher dimension that we can't see. But it would be closed because it would be finite in space. It's also finite in time because the big crunch would happen at a finite time in the future, maybe 1 trillion years from now, something like that. So that's a possibility. If true, then we live inside of a universe-sized black hole. I'll say if true, because there's a big question about this. Now let's just think about what this means. Well, we could think of this as being like an event horizon because you can't escape from it. And if you shine light around, it would go all the way around and come back and hit you in the back of the head. So light can't escape from it. And so it satisfies all the criteria for a black hole. And so that means then that if we do in fact live in a closed universe and we wonder what it's like inside of a black hole, maybe all we have to do is look around us. We see what's inside of at least this kind of a universe-sized black hole. So this then is a closed universe. It's closed back around on itself so that nothing, not even light, can escape and eventually will smash back down. And perhaps then you'll get a rebound effect and a new universe. And what we call the Big Bang, or what we call the big crunch for this universe, the next inhabitants of that new universe could call a Big Bang. So that's possible. That's one of the possibilities. The other possibility, which is getting more traction right now, is that the universe will keep expanding forever. Now, if this is true, then gravity doesn't catch up with the expansion. It's called an open universe. And because it just keeps getting bigger, it'll be infinite in space and infinite in time. Now, which one do we live in? Well, the measurements that we make can't quite tell the difference right now between an open and a closed universe. It's very close to the critical point. And so we have gone back and forth with this. And at the present time, we think it's open. Okay, so today, most people would say it's open. I think that would be true. But 10 years ago, everybody was pretty sure it was closed. 10 years before that, everybody's pretty sure it was open. So they've been kind of a little bit schizophrenically going back and forth between open and closed for a long time. And so we don't maybe want to jump on the open bandwagon too quickly here, just given the history of our uncertainty and our inability to make up our minds as new information comes in. But one of the things that people look at today that makes us think it's open is what's called dark energy. And so this dark energy is an unknown type of anti-gravity energy. Remember we talked before about anti-gravity and how we didn't know whether negative matter can exist. Well, this is this kind of effect. It's an anti-gravity effect that's accelerating the expansion of the universe. And so, how did we find this anti-gravity effect? We were looking at the Hubble constant, h. We were looking at type 1 supernova explosions, which should give us an idea of what the Hubble constant was in the past. And so we assumed that the Hubble constant was bigger in the past because gravity should be slowing down the rate of expansion of the universe. And so the goal of this experiment was to find how much smaller was how much bigger was the Hubble constant in the past than it is today? And that would tell us how much gravity is slowing the rate of expansion of the universe. But what they found is that the Hubble constant was smaller in the past and is getting bigger. Which means that it was smaller in the past. And so this was the opposite effect that they were looking for. They discovered this, and a lot of scientists backed it up, but what they were looking for was the exact opposite. They expected H would be bigger in the past. And that gravity was slowing the rate of expansion and therefore making the Hubble constant smaller. But the only way that we know of to explain this is to say that the universe is accelerating. So this is evidence then for the dark energy. What is dark energy? Well, again, we don't know. But it's some anti-gravity type of energy that seems to act at larger distances. So the distances between galaxies, if you double them, you'd have more dark energy and more expansion. And so the galaxies then are feeling this effect at farther distances away and not so much at closer distances. And so it's thought that this dark energy started to make its presence known in terms of observational evidence about 5 billion years ago. So that's the point at which the Hubble constant started getting bigger. Now, if it continues to get bigger at this rate, and it doesn't slow down, then eventually we think the universe will just tear itself apart. That it'll become so much greater than gravity that planets won't be able to orbit around stars, and then as it continues to act for longer and longer periods of time, eventually not even atoms will be able to hold together. The electric forces will be overwhelmed. Then space itself will just be torn apart, and the end of the universe will be what some people call the Big Rip. Okay? And then basically space and time will just tear apart. It'll go flying apart in some way that we don't fully understand. And that could be the end of the universe then, in this scenario where it's an open universe. However, if H doesn't continue to get bigger at that rate, then the universe will just keep expanding, everything will get darker and colder, and eventually all the stars will fizzle out, and everything will pretty much just turn into black holes. But then the black holes, over even longer eons of time, will evaporate. There's a quantum mechanical effect that allows black holes to evaporate at a very slow rate, and that's called Hawking radiation. So in the very distant future, the black holes then would just evaporate and become photons of light. And that would be the very cold, dark end to the universe.